Hello and welcome to today's science lesson. So first of all, guys, can we all turn to wave and say a big hello to our friends on camera? Hello. And we'll begin by doing our meditation sequence. So I will sit down, take 2 fingers, find our heart center, left hand on our laps, and close our eyes. When you're ready, guys, you can open your eyes and come back to the room. Excellent. And next we'll do our stretch sequence. So let's stand up and push in our chairs. And we can begin by stretching up high to the sky, high as we can. And then let's go down low. Touch our toes. Back up high one more time. And this time, can we go tippy-toe high? And while we're there, let's have a wave side to side. And then back down to touch your toes again. Okay, guys, and now for some rotations. Left, right, left, right. Left, right, left, right, left, right. Now we'll do some stretches. 5 to our right. 1, 2, 3, 4, 5. Excellent, guys. And then we'll do 5 stretches to our left. 1, 2, 3, 4, 5. Excellent. And to finish, guys, let's do 5 claps. 1, 2, 3, 4, 5. Excellent. Have a seat. And now we've reached the end of the gravity section of our science lessons. So what we're going to be doing today is having a review about the sections that we've learned about gravity, guys. So first of all, let's write that word on the board. How do we spell gravity? G-R-A-V-I-T-Y. And remember, the other term that we can use for gravity is gravitational force. And that's slightly longer. Gravitational, G-R-A-V-I-T-A-T-I-O-N-A-L. Gravitational force. And what this means is, this is the force that keeps everything on planet Earth close to the ground. In fact, the force pulls everything into the center. But because we have floors, we stop at the floor. But if there was a hole in the floor, I would fall into that too. We would keep going to the center of the earth because of gravity or gravitational force. So let's say these words together, guys. Gravity and gravitational force. And what we're going to be doing today is having a review lesson of what we've learned previously. So who can remember some keywords or some aspects of gravity and gravitational force that we've learned before? Force. Yes, force, definitely. We've got force here. So we can write the word force again. F-O-R-C-E. And what we mean by force is the invisible thing that is keeping us to the center of the earth. And there's some other words we've learned too. About motion, yes. Motion is the way that things move from side to side and up and down. And gravity and gravitational force certainly affects force and motion. Now, who can remember there was a good saying that we used regarding force and motion? Remember, if I was to take a marker pen and go like this, what happens? What goes up must come down. And that's the rule of gravity on planet Earth. What goes up must come down. We can say that too. So what goes up, W-H-A-T, goes up, must, U-S-T, come down. Yes, because this is the rule of force and motion. I use force to send the motion of the pen up, but gravitational force then brings the pen back down. So what goes up must come down. And then later on, in later lessons, we learned about some other key words too. Sometimes about when we step on the scales, what do we do? If I was to step on some scales, what am I measuring? Weight. Yes, we talked about our weight. And another word that is quite similar to weight, but the same, mass. Yes. Okay. Now these two words, weight and mass, sometimes get confused. People think they're the same thing, but they're not. And we're going to do experiments today to prove how mass and weight are different. But remember, what does mass relate to? Yeah. Yes, mass, but what does it relate to? Begins with M2, sounds very similar. Remember when we learned about solids, liquids, gas, matter. Mass is the amount of matter in an object. M-A-T-T-E-R. Now, can mass change? Does my mass change? Now, what planet am I on? Earth. How about if I go into space? Does my mass change? No. Correct. Mass always stays the same. Mass does not change. Okay, but then we also learned about weight. Now, what has the effect on weight? And I'll give you a clue. The answer is here. But what changes the weight? The effect of gravity and gravitational force. Weight is affected by gravitational force. And can our weight change? Yes, our weight does change. Yes, because what we've got is gravitational force. So on Earth, we weigh a certain amount because of gravitational force. But is there gravitational force in space? The space on the other planets, do they have gravitational force? No. So therefore, our weight will change. In space, do we weigh more or do we weigh less? Less, correct, because the gravity is less and our weight will change and go up. So excellent, guys. Some very good points from our review of gravitational force. Our first word, force and motion, means that what goes up must come down. You must believe me. What goes up must come down. And with regards to weight, is affected by gravitational force. And weight can change. But what is different about mass relates to matter does not change. Okay? And today we're going to be doing some experiments. Today our students are going to take a trip into outer space, because we're all going to have them pick a planet each, or choose a planet. And what we're going to do, we're going to find out their mass on planet Earth, and then how to equate it to how much they would weigh on the other planets. But first of all, what we've got, guys, is a PowerPoint presentation for us to review the things that we learnt about regarding gravity and gravitational force. So let's turn to have a look at the TV screen to have a look at our PowerPoint presentation. So let's turn to the TV screen, guys. So let's take a look at our PowerPoint presentation, Gravitational Force Review. So let's take a look, guys, at the things we've learned before. When we jump into the air, we will always fall back to the ground. Remember, what goes up must come down. This is because there is a non-contact, invisible force acting on them. Can anybody remember the name of the force? Gravity, or gravitational force. Correct. Well done, guys. Gravitational force pulls everything towards the center of the earth. Believe me, if there was a hole in the classroom that went all the way to the center of the earth, you fall in, you go all the way to the center because of gravity. The reason you stop now is because of the floor. The floor keeps you here, but a hole, you would fall further. Leaves fall from the trees to the ground because of gravitational force. Water falls downwards at waterfalls because of gravitational force. If it wasn't for gravity, we'd have water ups. We wouldn't have waterfalls, we'd have water ups. Trees, water, buildings, and animals are all held on Earth by gravitational force. What would happen if there was no gravity in that picture? Where would the dog be? Sitting on the floor? The dog would be floating in the air. Where would this girl be? Would she be on the slides here? She'd be up in the air here. And as for the boy on the slides, his slides would be up here. Everybody would be in the air. No gravity. Without gravitational force, all objects on Earth would be floating around in space. Just like the spaceman here, the astronaut, he's in space. And as you can see, floating around. No gravity. Gravitational force controls most objects in the sky, but not all of them. Yes, can you remember? Some of them we don't control by gravity. An airplane can fly in the sky, but will always return to Earth because of gravity. A kite can fly in the sky, but will always return to Earth. But how about some objects that don't return to Earth? Clouds. Can we see clouds in the sky? Do the clouds ever come in the classroom? They're not controlled by gravity. Clouds are found in the sky and do not come back to Earth. Stars are found in the sky and do not come back to Earth. Why? Why don't stars come back? They're far away. They're what we call outside the Earth's atmosphere. Remember that word? Atmosphere. So gravity doesn't control them. Now, more about mass. The mass of an object is the amount of matter in the object. Yes, like we learned, or like we remembered earlier, mass relates to matter. The amount of matter in something, the amount of mass. The more matter an object has, the greater mass it has. What do you think has the most mass? The bowling ball or the pear? Correct. But why? Because it's heavier. Yes, it's lower. On a scale, the heavy thing will go to the bottom. We can see the bowling ball is heavier than the pear. The greater mass an object has, the harder it is to move. And that's what we mean by motion, the word we remembered earlier. Motion relates to movement. Something with lots of mass, heavy, hard to move. Like the guy, he's silly trying to push the car. Do you think he can push the car, Net? Can you push that car? No, too heavy, too much mass. The trolley is easy to move or change its direction when it's empty. Mass of the trolley becomes greater when it has matter in it. Now, which trolley is easier to move? The empty trolley or the full trolley? Yes, because less mass, more motion, easier movement. Therefore, the more mass an object has, the more it resists changes in motion. That's why it's easier to ride a bicycle than drive a bus. Which one has the least mass? The bicycle. So which one's easier to turn? The bicycle. The bus has lots of mass, very heavy. Takes ages to turn. If you try to turn a bus with the steering wheel, it can take forever. A bicycle, a lot easier. And then the next key word, weight. The weight of an object measures how much gravitational force is acting on it. So remember, gravity and gravitational force affects weight. Mass doesn't change, but weight changes based on gravity. A spring balance and a compression balance can be used to measure weight. Yes. Therefore, there is also more gravitational force acting on it. Our weight on the moon is less compared to our weight on Earth, because on the moon, less gravity. So why do you weigh less on the moon? And you can know now, this is because the moon's gravitational force acting on the person is less. So if you're in a place with less gravity, more weight. If you're in a place with more gravity, less weight. Okay? That's the relationship. More gravity, less weight. Less gravity, more weight. The mass of an object is the same in every place, but the weight can change. However, the weight of an object changes from place to place. That's why we weigh more on different planets, just like you're going to find out soon. Any questions, guys? That was brilliant. Very well done. Welcome back to class. We hope your students enjoyed the review PowerPoint exercise on everything we've learned about gravity and gravitational force, and the ways in which gravity affects weight but does not affect mass. And coming up, we've got an exercise for our students to practice how to take their mass on planet Earth and convert it into other weights on different planets. But before then, guys, time for our stretch sequence. So let's stand up and push in our chairs. Okay, and for this sequence, we'll start by doing some rotations. Left, right, left, right, left, right, left, right. Now let's take our right hand and find our left foot. And then left hand, right foot. Right hand, left foot. Left hand, right foot. Right hand, left foot. Left hand, right foot. Okay, guys, now let's stand up and shake it out. Shake it out. And now for some stretches. So 5 stretches to our right. 1, 2, 3, 4, 5. And then 5 stretches to our left. 1, 2, 3, 4, 5. And to finish, we will do 5 star jumps. 1, 2, 3, 4, 5. Excellent, guys. Have a seat. And now it's time for our experiment to find out what our students will weigh on different planets. So what we need to do first is we need to understand the equation to get our weight on different planets. And the equation that we need to work out, guys, is mass times gravity equals weight. Yes. Now the different measurements are taken as follows. When we look to get our mass, we can use some scales. And the scales we will measure in kilograms. Okay? So remember kilograms. Find out what our mass is first in kilograms. Then we have to find out what planet we need to find out the gravity on. And gravity is a force. And we times the kilograms by the amount of force. And then we get our answer of weight in, ready guys, newtons. A new unit of measurement that we're using today about our weight on the different planets using gravity, we weigh in newtons. So one more time, newtons. Yes, we know our mass in kilograms, but when we times our mass by the gravitational force, it gives us a weight in newtons. So teachers, for this experiment, one thing that you will need to use is a set of scales similar to this, because we're going to have our students come forward and weigh themselves. We need the mass and the weight in kilograms. And what you also need to do is print off the flash sheets for the lesson and cut all of the flashcards into individual strips of paper. They will have the names of the planets with the gravitational force written alongside them. And we'll have different students come forward, choose a planet, weigh themselves, and we can find out what they'll weigh on that planet. So ready guys? Ready for a trip into space? Ready to go to another planet? Ned, did you bring your spacesuit today? Good, because you're going to another planet soon. So the first student, what way should we start today? Bangpon. Come and join me at the front of class. Bangpon gets first pick on a planet. Okay, so pick a strip of paper. Bangpon, what planet are you going to? Oh, Bangpon is going to the furthest away. Neptune. Neptune, okay. And what's the gravitational force on Neptune? What number can you say? 12. Okay, so we've got Neptune. In fact, I'll write this in black so we can see. So Bangpon is going to Neptune. And the gravitational force on Neptune is 12. Okay? So what we need to do now, Bangpon, can you stand on the scales? So let's stand up straight so we can get your weight. And let's see, in kilograms, 30 kilograms. Okay? So Bangpon's weight, or Bangpon's mass, sorry, is 30 kilograms. So if Bangpon is going to Neptune, how many times do we have to times 30 by? 12. So can anybody tell me, what's 30 times 12? Or 12 times 30? And that will give us Bangpon's weight on Neptune. Correct. And what are we weighing in? 360 newtons, yes. So Bangpon, if you go to Neptune, Bangpon will weigh 12 times more, because the rate of gravity on Neptune is 12. That was excellent, Bangpon. High five and a big round of applause for Bangpon. So teachers, you can see the activity that we're doing in our classroom. And what you can do now is you can pause the video and do the same activity with your own students. And remember to choose a different student for each planet. so that they can choose a different flashcard and find out what their true weight on that planet will be. And now it's time for Lakgao. Lakgao to choose another planet. So choose a planet, Lakgao, and show it to your friends. Where is Lakgao going? Jupiter. Okay. Wow. Jupiter. What is the rate of gravitational force on Jupiter? What number can you? 26. Okay. So Jupiter, 26. So Lakgao. What we need to do is Lakgao, can you stand on the scales for me? So what do we have? Okay, we've got around 45. Okay, Lakgao's weight on the planet of Jupiter is how much? We've got 1,170 newtons. So don't worry, Lakgao, that's not your weight on planet Earth. That would be your weight if you were on Jupiter, where the gravitational force is 26. So high five and a big round of applause for Lakgao. Now time for our next student. Prel, come and join me at the front, please. Time for Prel to pick her planet. What planet are you going to, Prel? What planet can we see? Mercury. Okay, what's so funny about Mercury? We've got planet Mercury. What's the gravitational force on Mercury? 4. Okay, Mercury, 4. And now it's time for Prel to take to the scales. Let's see what your mass is on planet Earth. What do we think, 25? Okay, 25 kilograms. Prel's mass on planet Earth is 25 kilograms. Okay, so if the gravitational force on Mercury is 4, we have to go 25 times 4. 100 newtons. Prel's weight on the planet Mercury would be 100 newtons, because 25 kilograms of mass on planet Earth times by a gravitational force of 4 on Mercury means 100 newtons. Prel, that was excellent. High five and a big round of applause for Prel, please, guys. And now for our next student, Dan. Come and join me at the front, please. Now it's time for Prel, it's time for Dan to go to another planet. But what planet will you go to? Mars. Not too far, the next planet to Earth. And what's the gravitational force on Mars? 4 again. Same as Mercury. So Mars, M-A-R-S. 4. Sit down. Now time to take to the scales. How many kilograms? 32. 32 kilograms for Dan. Okay, so if we take Dan's mass of 32 and times it by 4 for the gravity on Mars, what will Dan's weight in newtons be on the planet Mars? 32 times 4. 28. Excellent. 128 newtons. So Dan, very sorry, if you go to Mars, you're going to weigh that much, okay? Very good. Big round of applause for Dan. And now Chu's turn. Chu, come and join me at the front, please. Okay, so what planet is Chu going to? So let's see. Uranus. What's the gravitational force on Uranus? 9. Okay, so Chu, is going to Uranus. So now it's time for Q to take to the scales. Let's find out his mass on planet Earth. How many kilograms? 28. Q's mass on planet Earth, 28 kilograms. So who can tell me 28 times 9? Perfect. That's correct. Pak Bung. 252 what? What does the N stand for? Newtons. Yes. So Q, if you go to Uranus, you will weigh 252 newtons. So high five. Big round of applause for Q, please, guys. And now time for Nadia. Nadia, come and join me at the front. So Nadia, what planet are you going to? Venus. Okay, 9. So we can put Venus, gravitational force of 9. But Nadia, now we need to know your mass in kilograms on planet Earth. So let's see. 31. 31 kilograms is Nadia's mass. So 31 times 9, guys. 279. 9 times 31 is 279. So Nadia, your weight in newtons on the planet Venus is how much? 279. Okay? So high five and a big round of applause for Nadia. And now it's Pat's turn. So Pat, pick a planet. Okay, show it to your friends. Earth. This planet. Okay? So when we go for Earth, what is the rate of gravitational force on Earth? 10. Okay. So now what we'll do is we'll take Pat's mass in kilograms on Earth and convert it into newtons. So 30 kilograms for Pat in mass. Okay? So 30 times 10. Okay, so on planet Earth, now, because we're on planet Earth, what is Pat's weight in newtons? 300 newtons. So Pat is the one who knows what his weight is now, because he's the one on planet Earth. So excellent, Pat. Very well done. And now, time for our final steward with the final planet, Pak Bung. So Pak Bung will be going to show your friends. What planet? Saturn. And Saturn has 11 newtons. So let's see, can we find a space for Saturn? Saturn will go at the top. 11 gravitational force. So now, Pak Bung, can we find your weight in kilograms? 30. Okay. So Pak Bung, 30 kilograms of mass. But on Saturn, what would Pak Bung's weight in newtons be? A gravitational force of 11 and 30 kilograms. 330 newtons. Okay? So Pak Bung, what is your weight in newtons on Saturn? And 30. Excellent. Very well done. Okay, so big round of applause for Pak Bung. So now we've got all the planets, but we still need to weigh one more student. So Net, come and join me at the front. You need your weight for your worksheet. Okay, so Net, can you stand on the scale? Okay, Net, 62 kilograms. Okay, so Net, what I'll do, I'll put your weight here, 62 kilograms, your mass, okay? So when you come to do your worksheet, what you need to do, guys, is take your mass in kilograms and convert it using the gravitational forces. So well done, Net. Big round of applause, guys. Very well done. And now it's time for our worksheet part of the lesson. So what we're asking our students to do is to convert their mass in kilograms that they all know now on planet Earth into the different weights using the gravitational force on the different planets. So what we want our students to do is, for the 3 columns, we need mass times gravity equals weight. Just like we've done here, guys, okay? So the 3 columns after planets, we've got mass times gravity equals weight. And then, using your mass, which you all know now because you've been weighed in kilograms, times it by the gravitational force on each of the planets. And that will tell you how much you weigh in newtons on each of the planets. But what's the first thing to do, guys? Write your names on top. So teachers, just monitor the class and help students with anything they need. But if they've been paying attention, all of the information they need, their weights, the gravitational force of the planets, is there for them. And they just need to work out their own weights on each of the planets. So Net, this one's for you. You're welcome. Pat, for you. You're welcome. Nadia, for you. You're welcome. Chu, there's yours. You're welcome. Dan, for you. You're welcome. Prel, there's yours. You're welcome. Black Owl, for you. You're welcome. And Bangpon, you're welcome. So names on top first, guys. And then remember, in your 3 columns, mass times gravity equals weight. And then take your mass that you've worked out already and work it against the gravitational force on each of the planets. So here we have mass times gravity equals weight. That's what you're doing your calculation based upon. So you know your mass, you've all got your own masses now, and you can then convert it against the gravitational force of each of the planets. So what you can do, guys, is you can put your own weights or your mass against the gravitational force of the other planets and work out your own weight in newtons, just like we've been doing with the flashcards exercise. And remember, the calculation that you need to do to head your columns, mass times gravity equals weight. That's it. Pakbong Ektin. So mass, and then the times symbol, gravity equals weight. Yes. Mass times gravity equals weight. It's the equation we've been doing. Mass times gravity equals weight. So in them 3 columns, Prel, you need mass times gravity equal weight. What teacher has written in blue is what you should write on your columns. So, what's your mass? Your mass, does your mass change, Pakbong? Does mass change? No. Your mass is always 30 kilograms. So, in this row here, you will have 30 kilograms every time because your mass doesn't change. But then, you have to work it against the gravitational force of the planets to give you your weight in newtons. So for example, what's your mass? 30 kilograms. Okay, so you can write 30 kilograms here. And then what planet do we have? Mercury. So what's the gravitational force of Mercury? 4. So your equation for Mercury, 30 kilograms times 4, will give you your weight in newtons. Welcome back to class. We hope your students enjoyed the worksheet exercise where they had to take their mass that we've already worked out in kilograms and then times it against the gravitational force of each of the different planets. And then what that will reveal is the weight of our students on each of the different planets in newtons. And my students here have all done an excellent job. Quite a different topic to understand because mass and weight seem quite similar. But that was excellent, guys. Very well done. And that's all we've got time for today, which brings us to the end of our gravitational force section. So we hope you've enjoyed it and now understand more how gravity affects weight but will not affect mass. And we'll see you again soon for the next lesson. So can we turn to wave and say goodbye, guys? Bye-bye. See you again soon.